Assalamualaikum warahmatullahi wabarakatuh dan selamat sejahtera. Today we're going to learn on the feedback controller, proportional integral derivative or PNID controller. In this session, we're going to learn on the most common used type of controller, which is a feedback controller. And the aim of this session is for you to familiar with P proportional, Pi proportional integral, or PNID proportional integral derivative controller. Controller, known as the brain of the control loop, it performs the decision operation in a control system. The operation of controllers starts with comparing the process signal it receives, which is the control variable, with the set point. After that, it sends an appropriate signal to the control valve or any other final control element in order to maintain the control variable at its set point. What we have learned in previous session is the component of control loop. It consists of the transmitter signal and then the controller and also the final control element. In order to design control system, we need to identify certain variables that are control variable, and then manipulated variable, and also the disturbance. For example, in the figure, variable that we want to control is temperature. Okay, it's clearly seen on the control loop here is the temperature of the outlet stream. This is your control variable. And then the variable that cause fluctuation of the temperature is the temperature inlet or the flow rate of the temperature inlet. This is your disturbance. Okay, and then the variables that correct any deviations of the control variable in this figure is the steam in, and it is also known as the manipulated variable. When temperature deviates from its set point, the deviation signal will be measured by the transmitter. Here, if any deviation, for example, the set point is 70 and it reduced to 60, for example. So the deviation measured by the transmitter signal, and then the transmitter send the signal to the controller to make a decision based on mathematical equation whether it is the first order, second order, or higher order of the reaction, and translated by the transfer function and transfer the corrective measure to the final control element, also known as the valve. Okay, this is the final control element, also known as the valve. Afterwards, the valve is then open or closed as instructed by the controller. So fully open, known as 0%, 100% percentage, and fully closed of the valve is known as 0% of the valve. And the valve finally maintains its position right after control variable reach its set point. And then this figure shows the closed loop. Okay, closed loop of the feedback controller. Why do we call this one is closed loop? Because because any deviation from set point was corrected by the use of the controller. Alright, as opposed to the open loop system, human intervention is needed to take any corrective measure. So the closed loop and feedback controller is the most common type of controller used in industry. There are two types of the action of the controller. The first one is the reverse action, and the second one is the direct action. So what is the direct action? So when an increase in signal to the controller requires an increase in controller input. Okay, whereas for the reverse reaction, when an increase in signal to the controller, it requires a decreased controller in an output. Action of the controllers is best described in this case. For example, the heat exchanger in a controller. Alright, so the signal from the temperature transmitter is increased. Alright, and increase as you can see from the figure, indicating that the outlet temperature has increased above the set point. So temperature increase above the set point. To return the temperature to the set point, the controller must close the steam valve by some amount. So we need to close your valve to some amount. And then the controller must reduce its output signal to the valve. And then this condition, when an increase in signal to the controller requires a decrease in controller output, so the controller must be set in a reverse action. Then we move to the second type of the action of the controller. For example, this level controller. So signal from the level transmitter increase, indicating that the level in the tank has increased above the set point. So this is the level controller. So the level has increased. To return the level to the set point, the controller must open the steam valve by some amount. So it requires the output of the controller to increase. So the controller must increase its output signal to the valve. So in this kind of action, when an increase in signal to the controller, increase in signal controller, and increase in the controller output, the controller must be set in the direct action. So this is the example of the direct action. How do the feedback controllers work? It works, the feedback controller make a decision by solving an equation based on the difference between the control variable and also the set point. So in feedback controller, so the objective is to reduce the error signal to 0. This is the error signal. Error signal is basically the differences of the value in set point and also the value in measured of the control variable. So basically this is the signal received by the sensor and also transmitter. So we want to reduce the error approximately 0. When the error is equal to 0, that means set point and also the measured value is equal. That's what we want to achieve in the controller. Okay, figure show the conventional block diagram of the controller. So this is your controller, feedback controller. So as I mentioned earlier, this is the error that we want to reduce. Error is produced by the differences of the input measure by the sensor transmitter and also deviation from its set point. Alright, so this is the error. And PS known is the output of the controller, and GC is the transfer function that describes how the controller acts on an error. Means transfer function is the mathematical model derived for the process in order to make any decision when error has occurred. Proportional control is one of the type of the PID controller in a feedback controller. So for a proportional control, the controller output is proportional to the error signal. So PT is the controller output, P cap is the bias, which is at steady state value, and it is usually set at mid-scale of the controller output at 50%. KC is the controller gain, usually dimensionless, and E is the error. Alright, so P bias value is equals to the controller output when the error is 0. Alright, P controller output is equal to bias in steady state when the error is 0. So the proportionality is given by the KC, controller gain. The controller gain determines how much the output from the controller changes for a given change in an error. Previously, from the proportional control equation, the controller output is equals to bias plus controller gain times the error of the controller. So in either behavior of the linear equation, y equals to mx plus c, where c is the bias, m is the slope, kc slope of the controller gain, and e as a function of the x, and p is a function as y. So the ideal behavior of the proportional control is as shown in this figure, but in the actual behavior, basically the output controller will have the minimum and the output value. The key concept behind proportional control are the following. Upon a load disturbance or a change at the set point, the controller gain can be adjusted to cause a quick change to the control valve. The sign of Kc can be chosen to make the controller output increase or decrease as the error signal increases. The controller setting is considered acceptable if the process response is within the quality limits. The controller gain, which is the Kc of the proportional control, can be made either negative or positive value. So the general equation for the proportional control is equal to the one in the green box, which is the Pt. Pt is the controller output minus P cap bias equals to Kc is the controller gain, and also this one is the error. The action of the proportional control can be either in a reverse action or the direct action. The reverse action, the proportional control is said to be in reverse action when Kc value larger than 0. So the controller output increases as input signal decreases. This is the reverse action of the proportional control. Whereas for the direct action of the proportional control is when Kc value is less than 0, because the controller output increases as the input signal increases. Figure shows the process response curve of the proportional control with different controller gain value, which is the one in the black color have a very considerably high controller gain, Kp is equal to 2, whereby for a red line process response curve, it has considerably low controller gain, which is Kp is equal to 0.5 of the proportional control. So it is stated that a high proportional gain results in large change in the controller output for a given change in the error. So if the proportional gain is too high, the system can become unstable. It can be observed from the process response curve of this black line. What we can observe from this figure is the process response curve become oscillated around the set point. Whereas for the controller gain value that is too low, the controller action may be too small, hence it have less responsive to the controller, so it become less sensitive, and it is due to the small gain result in a small output response to a large input error. The advantages of the proportional control, it only has one tuning parameter, which is the controller gain Kc. as compared to the other type of feedback controller. And whereas for the disadvantages, proportional control will not settle at its target value, but we retain a steady state error that is a function of the proportional gain and the process gain. So that means the process response curve will behave in an offset type of process response. So the control variable operate with an offset, which is the steady state deviation of the control variable from the set point. The process response curve is said to be offset when it cannot reach its set point. So this is your set point. If you can refer from the figure, at any given KC controller gain for the proportional control, the process response curve would not settle to the set point. Some other type of controller are not using controller gain. Instead, they are using the proportional gain. Proportional gain, which is the PB. And in order to calculate PB, you must follow this equation. PB is equal to 100 divided by KC. For the transfer function for an ideal proportional controller is the controller output divided by controller input and equal to the controller gain, which is KC. KC is the dimensionless. Try to solve question 1 and submit to the GC. The controller is a proportional only controller with the gain of 2.5. Its bias value is set at mid-scale. The set point of the control variable is 20% TO. Calculate the controller output if the input signal to the controller is 30% TO. So try to solve this question using this equation. Now we're going to learn on the second term of the PID controller, which is the integral term. So for integral contraction, the controller output, which is the PT, depends on the integral of error signal over a unit of time. So this is the error signal over the time, and this one is the bias. Okay, tau I indicates the integral time or a reset time, where it is an adjustable parameter to the integral term in PID controller. So integral control action is widely used because it provides an important practical advantage and the elimination of the offset as compared to the P on the controller. Integral control action is normally used in conjunction with proportional control as the proportional integral controller. Alright. And the general equation of the controller output for the PI controller is given by this equation, where controller output PT is equal to P bias plus KC is the controller gain, ET times error. This is the P term in the PI controller, and whereas this one is the I term in a PI controller. So when the error is introduced at t equals to 0, the controller output change immediately by an amount equal to controller gain Kc. So this is the response due to the proportional mode. Under PI controller, as long as the error is present, the controller keeps changing its output, which is the integrating the error. Once the error disappears, which is goes to 0, the controller do not change the output anymore, whereas whereby it integrates a function with a value of 0. The corresponding transfer function for the PI controller is given by this equation, where we know that for PI controller it has two parameters, which is the KC, controller gain, and also tau, integral time or reset time, tau I. So this is the transfer function for PI controller. P divided by E is equal to KC times 1 plus 1 over tau IS, or equal to KC tau 1S plus 1 divided by tau IS. Figure shows the response of liquid level process under P proportional only controller, and also the proportional integral controllers. So what we can observe from these two types of process response resulting from two different type of controller, if we can observe from the P only controller, the result of process response curve will behave in offset condition. Alright, that's mean offset condition. So this kind of process response curve, it will not reach the set point set here, which is at 6 feet. In contrast with the PI controller, the process response curve will initially oscillated, and finally it will reach the set point and achieve the steady state condition. In an ideal condition, when there is a changes of the set point SP to SP2, the other response will look like the one represent here in dotted line. So this is the ideal response. When there is a change in set point, the process response curve will change exactly like the step input changes. Unlike the P only controller, proportional only controller, the process response will be resulting in the offset. Hence, in order to eliminate the offset, we will introduce the I term in PI controller. So basically, the I term, which is the integral time, is used to drive the process toward the set point. So it is stated that a decrease in I makes the controller action more faster or more aggressive. So this is the example of the process response of the PI controller with a different of I value. So if you can see the green line, I is not strong enough to drive the process toward the set point. Hence, we need to decrease I much lower from the one that we did in green line. And it is just nice to produce the good result of the process response curve. However, if we reduce furthermore, which is reduce furthermore the I value, the process become more oscillated as represented as the red line. So what we can observe from the figure in the slide is the steepness of the response curve increase with the decreasing in I. So you need to very careful in order to lowering the I value in order to obtain the optimum process response curve. So decreasing too much can cause I value can cause the present value to overshoot the set point value. So what we can conclude from the integral term of the PID controller. So basically PID controller has two parameters, which is the controller gain KC and also in reset time tau I. So the smaller value of tau I, the faster the controller integrates. Decrease of the tau I would enhance the controller ability to change. The formula of the reset time TIR is equal to 1 divided by tau I, tau 1. This is the equation to find the reset time. So what is disadvantages of the integral term in the PI controller? So basically, the integral term can cause a reset or integral wind up. So what is the integral wind up? Integral wind up is the situation where there is a integral term that being saturated in the controller. So how does the integral term is being saturated is basically due to the sustained error occur in the controller. The final term in PID controller is the derivative term. So what is derivative term is all about? So basically the function of the derivative is the capability to anticipate where the process is heading by calculating the derivative error of the controller. So in either derivative action is given by this equation. So the controller output is equal to bias P plus tau D, also known as the derivative time, and then the derivative of an error in the controller. So derivative control is used to reduce the magnitude of the overshoot. So basically we don't want the overshoot process response curve in our controller. Produced by the integral component and improve the combined controller process stability. So basically the derivative term in PID controller given the stability of the PID controller. So PID controller is used mostly in slow processes. For example, the temperature controller, because the process requires a longer time constant. The derivative term slow the rates of change of the controller output. The figure shows the process response curve of the PID controller in the heat exchanger. So if you can observe, the outlet temperature start to decrease when the inlet temperature decrease. So at time TA, the amount of the error is positive and small. So the control correction provided by P and I is also small. However, the derivative of this error, slope of the error curve, is large and positive. Control corrective provided by the D is large, and by looking at the derivative of the derivative of the error, the control variable is heading away from set point and use this fact to help controlling. So at TB, the error is still large and positive. However, the derivative of this error is negative and the error is decreasing. So the variable has started to come back to the set point toward the end of the process response curve. The D term or derivative term in PID controller, it helps to accelerate the process and also reduce the overshoot resulting from the integral term or I term. Increases the D makes oscillation period become more shorter. So as you can observe from this tree process response curve, it has different value of the D as the D value decrease as shown in red line process response curve. So as D decrease, the process response curve will have shorter time to reach the set point as opposed to the other two process response curve represented by the green line and also the blue line. What we can observe with increasing D, oscillation period become more shorter, and also it would reduce the overshoot, but slow down transient response, which is the rate of change of the controller output. For a noisy process, we need to avoid using D term in PID controller, or in other way, we need to use lower value of D. In contrast, D term or PID controller is good for slow processes like the temperature controller. As much as a lot of benefit of using the term in PID controller, we need to still give some consideration of not to given or increase too much D term, because too much D term in PID controller make controller action more faster, and it will resulting in instability of the controller. Now we consider the combination of the proportional, integral, and derivative control mode as in PID controller. So the form of PID controller is given by this algorithm. Controller output PT is equal to P bias plus KC. This is the P term, KC times ET. ET is the error, and then this is the I term, 1 divided by tau I, integral time. And this is the D term of the PID controller. This is the derivative time. And expanded form of the PID controller is given by this equation. Controller output is equal to P bias plus KC is the controller gain of the proportional term times ET plus KI. KI is the controller gain for the integral term in PID controller, and also the KD. KD is controller gain for the derivative term in PID controller. So finally, this is the corresponding transfer function for PID controller, where P divided by E, controller output, divided by controller input, is equal to KC, controller gain, 1 plus 1 divided by tau IS plus tau D times S. The comparison between these three controller type, which is the P only controller, and then PI controller, and also PNID controller. Alright, so we look at the P only controller first. This is the simplest form of the controller, and the tuning is based on the controller gain, which is the KC. This kind of controller will resulting in the offset, and it sustain disturbance or set point change. Next, we move to the PI controller. So as opposed to the P only controller, the PI controller resulting in no offset. However, it will cause a reset windup, and it is have two terms, which is the KC and also integral time. More complicated than the P only controller. However, it has a better performance than the P controller. The final type of the controller, which is the PID controller, among these three type of the controller, this is the most complicated controller because it has three term and we need to tune all those three term, which is the KC, tau I, and also tau D. However, it has better performance than the Dpi controller. And again, as opposed to the P controller, it has a similar function with DPI because it resulting no offset. And basically for PID controller, the most common type of the controller used is all those three term PID controller is the temperature controller. For the other process variable, the most common type of the PI of the controller used is the PI controller. Every PI and D term have different effect to the output response of the PID controller. In any disturbance and step input change event, the output response of a process without controller shown with this figure. The output response behaves way further the set point with no sign of approaching set point, which we try to avoid in any processes. The output response with proportional term, known as proportional controller, however, improve by searching for set point. However, faster response require higher proportional gain, thus contribute to higher error and instability in control system. The integral term discard the error produced while having the overshoot and reach set point eventually, as shown in this figure. And the derivative term in PID controller reduce the overshoot in the output response. However, the behavior of the output response becomes slowing down, which led to the instability in process control system. To solve question number 2, let us consider question A first. So you need to develop a block diagram, with transfer function of this controller. So for question 2A, you need to to get the transfer function for the proportional only controller. Alright, so transfer function for the proportional only controller, you may refer to the lecture notes. And then for question 2B, again you need to develop a block diagram of the PI controller with given gain and also the integral time. Alright, and then you need on question 2C, you need to develop a block diagram with a transfer function for PID controller with this given information. Try to solve question 2A, B, C and submit at the Google Classroom. That's all for today. Thank you and Assalamualaikum warahmatullahi wabarakatuh. See you in the next session.